me, right?
Yep. Yeah, take it away. Thanks.
Perfect. Cool. So thanks for having me. I'm Franz, and I'm a researcher at pdoom.org, and as well as TU Munich. And at pdoom, what we try to do is sort of pioneer truly open research on the path to AGI. And of course, this is sort of just a tongue-in-cheek adaptation of another mantra of one of the big labs that is sadly not as open anymore as they used to be. Specifically, we're going to talk about Jasmine, which is our word modeling code base, but also more broadly about pdoom as a research org and our research directions. So who are we? We're a Discord server. So essentially over 200 random people who are on a Discord server and work towards solving roadblocks that we need to overcome towards general intelligence. So the Jasmine authors in particular are Alfred and Meteor, who are also in the call, as well as myself and Stefan Bauer. So before actually talking about Jasmine, I'd like to sort of take a step back and reflect upon the state of AI research in 2025. So with the advent of the transformer, what people very quickly did, both at OpenAI as well as at Google, is they trained on the entire internet. And then at some point, people very quickly realized that this is actually not the distribution that you want the model to actually learn. And so people started upsampling data, for example, upsampling coding data. And also we unlocked a new data trove, specifically preference data, and used the new method, in this case, RLHF, to use the data trove. And with sort of these two techniques, upsampling and RLHF, on preference data, we sort of unlocked this capability of coding. So models became sort of useful enough to start using them for coding. Now, fast forward to last year, both OpenAI with their O1 as well as DeepSeek with R1 sort of showed that we can unlock another data trove, namely the data trove of verification signals, by simply doing reinforcement learning in post-training. And by unlocking this data trove and RLing our models in post-training, we sort of unlock the next set of capabilities. And this sort of culminated in the recent IMO gold medal from DeepMind and OpenAI. Now, what we're doing at pdoom is sort of, we're pondering day in and day out, so what's the sort of next set of capabilities that are going to be unlocked, and how are they going to be unlocked? And our sort of very naive and almost primitive answer to this is, well, you just train on such data. And I'm going to elaborate on this. So one of the things I want to convince you of in this talk is sort of that we have these two hammers. We have the behavior cloning hammer, so next token prediction, and we have the reinforcement learning hammer. And just these two hammers are pretty much enough to solve at least a lot of the sort of, or elicit a lot of the capabilities that we want these models to have. And then there's one third thing, which is you need the right data. So just to give you an example, so this is sort of a past example, the standard recipe for unlocked thinking is you capture, you collect sort of cold start data, which is essentially just long chain of thought data from humans, so data labelers, for example, and then you fine-tune the model on cold start data, on long chain of thought data, before doing reinforcement learning to hone into this new capability that was unlocked, as well as generalize it to other domains. Now, this is, of course, past work. So what about something that has not been solved yet? For example, here's a recipe for unlocking adaptive compute. Well, if you look at our two hammers and sort of finding the right data as the mental model to unlocking this capability, the sort of most natural thing to do would be to take a data set of chatbot conversations and let a model actually condense the answers, including chain of thoughts, to easy questions, and expand the answers to hard questions. And then you can fine-tune your model on this new data set. And this is actually something that a collaborator of ours is working on currently. And what about solving long horizon tasks? So there's another recipe for this, which also only makes use of these two hammers and the right data. And so the way to do this is just an example, is to bootstrap a product with mass adoption. This is, of course, the hard part. And one example of this is Cursor. And then what you can do is you can mine verification signals from user feedback. And then after mining these verification signals from user feedback, you can essentially train your model on these verification signals, and thus sort of incrementally lengthen the model's task horizon. And then you can redeploy the model and again mine verification signals. This is sort of one way of creating a feedback loop that lets you sort of lengthen the model's task horizon. And I mean, of course, the big labs are onto this, and this is the reason why, apart from APIs, sort of the main second big product of these big AI firms is nowadays CLI agents. And it's also the case why Cursor is valued so highly and why everybody wanted to buy Windsurf. Now, I talked about mining verification signals from chatbot conversations, but how do we actually do this? Again, same mental model, do the stupidest thing first. Well, you can just collect a human data set. You have to first realize that if we humans can determine implicit user verification, then so can models. And after realizing this, all you have to do is sort of collect human data for verification signal mining, fine-tune a model on this human data set, and then run your model over all of your chatbot conversations. So I've sort of almost given you a roadmap to sort of spiky AGI for certain domains. In this particular case, this is coding, but what about other domains where it's sort of less obvious? With browser use, for example, you see the same thing playing out. So Claude has this Claude for Chrome Copilot, and they're trying to do the same exact playbook. But what about, for example, robotics? There it's completely unclear, and it's not feasible, at least not currently, to bootstrap your Copilot. So again, think back, we have two hammers. We have the behavior cloning hammer and the reinforcement learning hammer. So what would be sort of the behavior cloning way to do this? Well, worst case, Mark Zuckerberg, so Meta or Google, sort of collects human behavior data from smart glasses. So you convince your users to give you all the sort of video streams, and then all you have to do is behavior clone a robotic policy from videos of human behavior. Of course, this is an open research direction, but we think it's a very important one. Now, what's the alternative? Sort of the reinforcement learning way to do this. Well, there's also already this collection of internet scale video data sets. So what if we just train a world model on this internet scale data set and then train agents in these world models? And this is sort of what, for example, Genie is doing. And Genie 3, for example, is a very, very impressive release. However, we're not completely sure whether this will actually scale to the real world. This is sort of the research question that we're trying to address. So what we're trying to do is, we're trying to answer the questions, how do requirements, so compute and data requirements, scale with environment complexity? And to be a little bit more specific, you can read a little bit more about this on our blog post. But essentially what we do is we train world models on sort of toy environments of increasing complexity. So for example, Atari, RetroDream, Minecraft, and so on. And then what we do is we train the world model until it has sufficiently well modeled the actual environment. And we test this by training an agent in the world model and training another agent in the actual environment, and then testing in the actual environment. And then the performance difference must not be larger than K. And we have to define K. And we do this for multiple environments. And then sort of what we want to, at the end of the day, have is sort of like this requirement scaling trend. And from this scaling trend, we want to be able to sort of extrapolate whether it is, considering Moore's law, whether it is sort of feasible to scale this to the real world or not. And now we finally get to Jasmine. Jasmine is sort of our world modeling code base. So we coined it a simple, performant, and scalable JAX-based world modeling code base. And it's sort of the first milestone towards answering this question. So Jasmine is actually a fork from another repository by Matthew and Tim and Willie, who are at Oxford. And they sort of laid the groundwork for this. And I think Jasmine is pretty cool because we use a completely Google native stack. So Flex, Orbex, Optex, Grain, Pix, every record. And this means we have pretty much no other sort of non-Google external dependencies, which means that you sort of only have to verify that our code is correct. And hopefully you don't have to verify further down the line, which is usually the case with other code bases. Another one of the main features of Jasmine, and this is thanks to JAX, is sort of super easy to both shard and scale models. So switching from one a distributed scheme to another is essentially just changing one line of code. And also, thanks to JAX and Grain, Jasmine is completely bitwise reproducible, which means that if you run your model twice, you get exactly identical training curves. There's also a whole suite of other things that we did. So of course, you're using flash attention, but we're actually not using the flash attention library, but we're using cuDNN's optimized flash attention. And turns out that there is a code path from Flex to JAX to cuDNN that permits you to use flash attention if you fulfill some requirements, and we do. Also, host memory offloading is just sort of one additional line of code. We use Shazir suffix notation for increased readability. We use the new Flex and NNX API, and then also index shuffling and process parallel data loading, so that data loading is not the bottleneck. Asynchronous checkpointing, mixed precision training, and so on. And maybe one more thing to highlight is that we support TreeScope. And if you don't know TreeScope is a model inspection library from DeepMind. So if you go to our README, or to the README of our repository, you'll find a link to a demo notebook. And this is just a screenshot from our demo notebook. And this is actually, the demo notebook sort of depicts one workflow that we actually had. So we had a training instability, and then we wanted to check what exactly was the reason for this instability. And because we used TreeScope, we just sort of printed the model after a forward pass. And as you can see, we can conditionally enable capturing logits, attention weights, and activations. And then we can just visually inspect for example, in this case, logits. And in this particular case, we immediately realized that the training instability was that the magnitude of the logits was growing throughout training. And I think I need to emphasize that this is, we didn't have to write any additional code for this. This was just completely native. And all we had to do is print our model. So this was almost everything I wanted to say about Jasmine. However, there's one more thing, which is that we not only released the code base, but we also captured every single keystroke during Jasmine development, and we also openly released this dataset. So this might sound funky to some, so I'm just going to give you a little bit more context. So if you look at our broad research directions, you immediately see that sort of data is the primary thing that we're looking at. And it turns out that there are, for example, no good chatbot conversation data sets in the open. And at the same time, companies like Cursor and so many more are getting so much data from the open source community. So I think it's really time for us as a community to start crowdsourcing our data sets. And then we thought about what the sort of way to crowdsource datasets is that has the sort of least threshold to participate. And what we realized is we can just make an IDE extension. So we just quickly made a VS Code/Cursor extension that allows anyone to participate in crowdsourcing. And specifically what we do is we capture sort of the entire software engineering workflow. So we capture every single character level insert. We capture every file change, we capture autocomplete, we capture terminal invocation, and so much more. And this is sort of the data set from which the first version we have released already, which is just our data from Jasmine. And this extension is already available, and there are already some people that participate in this. So we already have a sizable data set. However, we have not released this yet because we still have to clean it, and we take this very seriously. But I think my call to action would be, if you want to contribute to sort of crowdsourcing such a software engineering data set, please do install the extension if you're writing open source code anyways. The one thing to actually realize here is this is actually data of humans working on tasks for days to months. So, and I honestly don't know if there's any other open data set where this is actually the case. So this might be sort of a novum. Now, so much about sort of the extension and Jasmine as a code base. I want to talk a little bit about JAX, because this might be something you might be wondering is, why did we do this in JAX? So the primary reason is, of course, well, the foundational, so the upstream repository was already in JAX. But from what I can tell, from what we can tell, there's sort of like a good side of JAX, a bad side of JAX, and a sort of ugly side of JAX. So the good side is, and this is sort of the killer feature of JAX, is that you can technically write code for a single accelerator and then let the compiler insert communication collectives automatically. So this means you can just scale from a single GPU to hundreds of GPUs without changing a single line of code, in theory. And also, JAX completely hides the Python overhead because it uses asynchronous dispatch. And I think the second sort of killer feature is that there are reference implementations from sort of world-leading researchers available. So, for example, Big Vision from Lucas Bayer and his team, or MaxTex from Rafi Witten and his team. What are the bad parts? So I mentioned that you can technically write code for a single accelerator and let the compiler insert communication collectives. However, if you actually want to write code and maintain code, you will quickly realize that what you write is not what you get in this scenario, which means that even if the compiler does it for you, you have to have the mental model of the communication collectives that will be inserted anyways. And at that point, you might as well just write the communication collectives down explicitly, which of course JAX also allows. And also the second thing is, JAX essentially introduces a new programming model, and you really, really have to internalize it. So that's why I sometimes say that JAX is almost more reminiscent of learning a new programming language than using a new library. And what is sort of the ugly part of JAX? Well, this is only about JAX on GPU. So JAX on GPU is generally fine, and you can actually make it performant if you add a whole suite of XLA compiler flags. But it's all documented online, so this part is not a problem. However, the part that's problematic is that the JAX profiler, called XProf, which is generally awesome, often gives wrong statistics on GPU. This actually means that the JAX profiler is sort of useless on GPU, which means you either have to profile yourself manually, or you have to use NVIDIA's profilers. So for example, Nsight Compute and Systems. All right, so this is already the main part of the talk. Just a few more hot takes that we can debate, sort of just to pick your brain. This is all sort of like about other research directions that we're thinking about. So one of the things is that, at least I personally believe that in the current regime of LLM post-training, reinforcement learning might not be the most natural paradigm to use. So what do I mean by this? In classical reinforcement learning, we had dense rewards, and we also had non-binary rewards. Whereas in at least current LLM post-training, the rewards you only get at the very end of the trajectory, and the rewards are usually just binary, so 0 or 1. And I actually believe that, and it's also the case that in classical reinforcement learning, if you were using binary rewards, then the model basically just stumbled upon a solution, and only then it could sort of optimize the trajectory towards that solution. Looking back, this is sort of dumb, but there was no other alternative. Whereas now with LLM post-training, this is sort of different because we already prompt the models with their sort of goals. So it's already sort of goal conditioned. And I think we might need to sort of hone into goal conditioning more. Like, for example, you could technically get rid of all reinforcement learning algorithms in post-training and just use expert iteration instead. So expert iteration is just rejection sampling fine-tuning, for example. And it would be sort of very interesting to see how far you can just take rejection sampling fine-tuning as a sort of baseline against reinforcement learning algorithms. But the other thing is, we think that continual learning should also be goal conditioned. So the sort of prime example for this is a paper by OpenAI, an old one, where they pre-trained sort of a policy a Minecraft policy, and then they fine-tuned this Minecraft policy using reinforcement learning. And what they did is they essentially had this hard-coded curriculum of, let's say, verification signals. For example, the model gets a reward after mining wood, after mining diamonds, and so on. And then, well, what researchers very quickly realized is that there will be catastrophic forgetting going on if you don't use an additional KL divergence to the base model. And we fully believe that this is actually only the case because the model does not, without goal conditioning the model, without giving the model sort of the long horizon, the long-term goal, the model does not know what knowledge to retain and what to forget. So I think there needs to be sort of a shift in research direction in the continual learning area. And the third thing is that I actually think that sort of the brute force way of credit assignment using approximate gradients will fail as trajectory length before verification grows. So there are a few assumptions here. So one assumption is verification is only at the end of the trajectory. And the second assumption is that the reward is only binary. That's why it's called verification. But right now, what we're essentially doing is we're using an approximate gradient, which is not even the true gradient. And to me, at least intuitively, it makes sense that the longer the trajectory before verification, the more likely that this sort of credit assignment will fail. Now, the question is, what is the answer to this? And my answer to this would be it's a model-based credit assignment. So just like we as humans use our human prior to assign credit to actions that we have done in the past, so will the models, I think, in the future. Now, this actually means that the most natural way of doing this sort of credit assignment will be in token space, which means that maybe continual learning will also be in token space. But we can debate this maybe in Q&A afterwards. Cool, and this already wraps up my talk. Please join our Discord server. Just go to pdoom.org or scan the QR code, and please install Crowdcode if you want to participate in crowdsourcing a data set. And also, if any of this interests you, please hit us up. We would love to collaborate because we're really just constrained on manpower right now. Thank you.